Hello students, welcome to EPG Pathshala. I am Dr. Ayushi Paliwal from Deshbandhu College, University of Delhi. So students, today we are going to discuss about the module Solid Phase and Hybrid Electrolyte Materials for Redox Flow Batteries from the paper Energy Related Materials. So students, let us see what are we going to learn in this module. First, what are membrane-less redox flow batteries? Second, the working mechanism of solid phase electrolyte materials in RFBs. Third, we will be discussing what are the hybrid electrolyte materials, and lastly, the importance and the need of hybrid electrolyte materials for RFBs. So, let us start with a brief introduction about this module. According to the phases of electroactive species, RFBs may also be classified as solid phase RFBs. Such systems do not require any ion exchange membrane or the separator, as the chemical energy is stored in an active material on the electrode plates. Hence, during the charging process, the energy can be stored as the electrode deposit at the negative and the positive electrodes, and it can be released by the dissolution of the electrode deposits during the discharge process. Several flow battery systems of this type have been developed, and they will be discussed one by one. Most of such systems, a single electrolyte is circulated through the cell and no ion exchange membrane is required. Hence, as the system operates without a membrane separator, it evades the problem of cross-contamination of the species through the membrane, and this nature of such batteries harshly hindered other flow battery technologies. However, this technology minimizes the cost, the design complexity of the batteries significantly. These features avail these batteries for attractive energy storage in large scale applications. Soluble Lead-acid RFB. This is a flow battery based on the electrode reactions of Pb2 in methane sulfonic acid. Similar to a metal or metal oxide flow battery, soluble lead-acid flow RFB does not require a separator, since single active or soluble species Pb2+ is present in the electrolyte, as evident from the figure. The electrode reaction takes part in the conversion of soluble or active species in solid species. The electrode reactions involves the conversion of soluble species, that is Pb2 plus, into solid lead phase or Pb phase at the negative, and solid lead oxide PbO2 phase at the positive electrode, respectively, during charging and discharging cycles. The charge-discharge reactions for both the half cells are shown as follows. At the positive electrode, Pb2 plus twice of H2O charges and discharges to give PbO2 plus 4H plus 2 electrons, with the energy of plus 1.49 volts versus SHE. At the negative electrode, Pb2 plus 2 electrons charges and discharges to give Pb, or the lead, with an energy of minus 0.13 volts versus SHE. Now the overall reaction becomes 2 Pb2 plus 2 H2O to give PbO2 plus Pb plus 4H plus. So this overall reaction describes the soluble lead-acid RFB. Dissolution and deposition of lead is a fast process that does not require overpotentials. However, the hydrogen evolution is observed in conventional lead-acid batteries during charge cycle at high SOC, which reduced storage capacity of this RFB system. Hence, to avoid hydrogen evolution, the methane sulfonic acid is used as the electrolyte. The chemistry of this system is different from the traditional lead-acid battery, where electrode reactions do not involve insoluble lead-2. The traditional battery gives charge efficiency of about 85% and energy efficiency of about 65% and an open circuit cell voltage of 1.69 volts. Whereas this RFB technology had been scaled up from few watt laboratory cell to a several kilowatt pilot plant cell containing 10 bipolar electrodes. This system faced few problems during its developments, such as dendrite growth of lead and shedding of lead oxide, which results in the significant loss in energy efficiency and also the failure of the battery. Further, it was observed that the phase structure of lead oxide has significant effects on cell performance. Generally, the pure alpha PbO lead oxide is preferred in this system, as beta PbO exhibits relatively loose structure, which results in the shedding of PbO. Due to lead acids combination of low cost, high efficiency, safety, and proven reliability, this innovative system has attracted much attention both from the academics and industry. Zinc-Nickel RFB. The zinc-nickel single electrolyte flow battery was first reported in 2007. In this system, a high concentration of zincate solution in potassium hydroxide was used as the supporting electrolyte. The charge-discharge reactions for both half cells are shown as follows. At the positive electrode, we have 2NiOH2 plus twice of OH minus 2 electrons gives 2NiOOH plus 2H2O. Whereas at the negative electrode, we have zinc OH4 2 minus plus 2 electrons gives zinc plus 4 OH minus. So the overall reaction becomes 2NiOH2 plus ZnOH4 2 minus gives Zn plus 2OH minus plus 2H2O plus 2NiOOH. During charge process, zinc is electrodeposited from the zincate ions at negative electrode and NiOH2 is oxidized to NiOOH at the positive electrodes respectively. The reverse process occurs when the battery discharges. This system has a high round-trip DC energy efficiency of 88% at 10 mA per centimeter square, and 1000 cycles have been achieved in comparison to the other two single flow systems. This system seems to be promising in terms of the cost and performance. However, similar to the lead dioxide system, the storage capacity is also limited by the electrode size. Zinc-Manganese Dioxide RFB. Now, students, we will be discussing about this type of RFB. Here, a single flow zinc-manganese dioxide RFB has been demonstrated using a flow-through packed bed electrode design rather than the conventional flow-by design. With the help of packed bed electrode design structure, an ion exchange resin is used as the separator material, and the separation between the two electrodes can be increased to avoid short circuit induced by the dendritic growth at the negative electrode. The discharge cell voltage of this system was reported to be of 1.2 volts, depending on the separator materials and the distances between the two electrodes. The charge-discharge reactions for both the half cells are shown as: at the positive electrode, manganese oxide, that is Mn2O3, plus 2H minus 2 electrons gives 2MnO2 plus H2O, whereas at the negative electrode, we have zinc oxide, that is ZnO, plus H2O plus 2 electrons to give zinc Zn plus 2H minus, 2OH minus. So the overall reaction becomes, which is done by just adding these two, is Mn2O3 plus zinc oxide to give 2MnO2 plus Zn. This table lists the operational parameters and performance of membrane-less RFBs. The parameters which have been listed over here are E0 versus SHE, where SHE stands for Standard Hydrogen Electrode. Next parameter is the electrode material. Next is electrode, which can be negative or positive. Here J has also been listed for all the redox couples, that is J is the current density, and eta, which is depicting the efficiency for all these redox couples. As you can see from the table, there is one parameter also, that is OCV, which is nothing but the open circuit voltage, and here AE and CE corresponds to anionic exchange and cationic exchange respectively. Hybrid electrolyte materials for RFBs. The redox flow systems based on the hybrid electrolytes involves different configurations compared to the earlier discussed systems. In hybrid RFBs, the active material can be introduced or removed from the electrochemical cell without deassembling the cell structure. Further, these systems do not store all of the active material in a liquid or a gaseous form. Hybrid RFBs involve the deposition in one half cell during the charging process. Zinc-chlorine and zinc-bromine are the best known example of these type of hybrid RFBs. Zinc is a typical negative electrode that has large negative electrode potential in both the acidic and the alkaline aqueous media. Hence, it has been used extensively in the batteries for a long time. Zinc-chlorine RFB. Energy Development Association, that is EDA in USA, developed Zinc-chlorine RFB for stationary energy storage applications during the early 1970s to mid-1980s. Charging-discharging process of this system is based on the electrochemical reaction between zinc, chlorine and zinc chloride aqueous solution, and the simultaneous chemical reaction between chlorine and water. The charge-discharge reactions for both half cells are shown as follows. At the positive electrode, zinc chloride, that is ZnCl2, aqueous solution gives zinc plus Cl2, zinc in the solid form and chlorine in the gaseous form. And at the negative electrode, the chlorine gas plus X times H2O gives the complex of the Cl2 gas dot X H2O, where X is approximately equal to 5.9. The above reactions are highly reversible, and the theoretical cell voltage of this system is 2.12 volts. During charge, the zinc chloride electrolyte is electrolyzed, results in zinc deposit on the negative electrode and chlorine gas evolution on the positive electrode. The chlorine gas got separated from the cell to another chamber where it is mixed with water at approximately 10 degrees Celsius that formed chlorine hydrated or Cl2.H2O. During discharge, the cooled chlorine hydrate is passed through a heat exchanger where it gets decomposed. The chlorine-rich stream is then pumped to the positive electrode where chlorine is reduced to chloride. Simultaneously, the zinc deposit is dissolved at the negative electrode. EDA's cell design is based on comb-like bipolar electrodes which incorporate low-cost electrode frames that can be injection molded to facilitate the manufacture and the assembly of the battery stack. The zinc electrodes and chlorine electrodes are made up of dense graphite and porous graphite respectively. Further, this system does not require separators as the solubility of chlorine in the electrolyte is very low. Hydrogen gas evolved at the zinc electrode gets converted to hydrogen chloride by fluorescent lamp attached to the battery. Japanese development on the same Zinc-chlorine RFB technology in 1980s and constructed battery modules of 1 kilowatt, 10 kilowatt and 60 kilowatt having energy efficiency of 71 to 76%, 66% and 63% respectively. The next type of RFB which we are going to discuss is Zinc-Bromine RFB. The zinc-bromine is another successful hybrid RFB system which has been demonstrated for decades. In this system, one of the electrodes involves non-liquid reactants. Hence, the combination of dissolved redox couples and metal anode brings great enhancement in energy density because the volume of analyte is eliminated. During charge, bromide ions are oxidized to bromine at the positive electrode and zinc is deposited at the negative electrode. During discharge, the reverse reactions occur. The charge-discharge reactions for both half cells are shown as at the positive electrode 2Br minus 2 electrons to give Br2, whereas at the negative electrode we have zinc 2 plus, that is Zn2 plus 2 electrons to give zinc. So the overall reaction becomes Zn2 plus 2Br minus to give Zn plus Br2. In this system, relatively higher concentrations of Br minus and Br2 can be utilized, enhancing both the reaction kinetics and energy density. However, the toxicity of Br2 and the highly corrosive nature of concentrated HBr are limitations. The toxic nature of Br2 can be reduced by utilizing complexing agents. However, the effect of complexing agents on kinetics has not been studied quantitatively, particularly in strongly acidic supporting electrolyte. In this system, ZnBr2 has high solubility over 2 molar. However, the charged species bromine 2, that is Br2, is less miscible in aqueous solvent, which substantially limits the achievable energy density of the zinc-bromine battery. Now students, we are continuing with the discussion over zinc-bromine RFB. Now furthermore, the stability of zinc-bromine redox flow system is challenged by the corrosive nature of bromine. Several redox couples have been examined to replace the bromine catholyte of zinc-bromine system. The figure shows the redox potential versus the SHE for various redox couples except the hydrogen evolution potential. Next type of RFB system is Zinc Cerium RFB. The Zinc Cerium RFB system was introduced in 2000s basically by Plurion inclusive by UK. It has a high open circuit voltage of 2.4 volts and has been claimed to be able to discharge at 400 to 500 milliampere centimeter minus 2. In this system, methane sulfonic acid is used as the supporting electrolyte and allows cerium ions to dissolve at higher concentration, that is greater than 1 molar Dm-3. Methane sulfonic acid was used in this system because it is less corrosive in comparison to sulfuric acid. Many researchers suggested that methane sulfonic acid can also reduce the zinc dendritic growth significantly. Further, Zinc Cerium RFB is a system which combines the very negative zinc couple with a very positive cerium couple to yield an open circuit voltage that is higher than any of its commercial competitors. An environmentally benign organic acid is employed as the solvent, and a common electrolyte system is used in both half cells. A zinc cerium battery containing carbon plastic anodes and platinized titanium mesh cathodes of 100 cm square geometrical area separated by a Nephron membrane was patented in 2004. Recently, an undivided zinc cerium RFB system using a single electrolyte at low acid concentration was proposed with the use of a carbon felt positive electrode and a mixed electrolyte of both zinc and cerium electroactive species. This membraneless system does not require high temperature of 50 to 60 degrees Celsius and can be cycled at room temperature with an average round trip DC energy efficiency of 75%. However, the optimum cerium-3 concentration was limited to only 0.2 molar per dm cube. However, higher concentrations could be attained by increasing the acid concentration, but this would result in poor charge efficiency at the zinc negative electrode due to the parasitic hydrogen gas evolution reaction. The charge-discharge reactions for both the half cells are shown as: at the positive electrode we have cerium 3 plus to give cerium 4 plus an electron. At the negative electrode we have Zn2 plus 2 electrons to give zinc or Zn. So the overall reaction becomes Zn2 plus 2 cerium 3 plus to give zinc Zn plus 2 cerium 4 plus. Now let us discuss about the zinc ferricyanide, zinc air and vanadium air RFBs. A zinc ferricyanide RFB was first introduced by Adams in 1979, in which zinc has negative electrode potential and the ferrocyanide couple are highly reversible in an alkaline medium. The experimental open circuit voltage was stated to be 1.86 volt, which is larger than the theoretical value. Second RFB is our zinc air RFB. This system with a circulating electrolyte containing zinc slurry was carried out in USA, France and Japan. In zinc air flow batteries design, regeneration of the zinc slurry is performed outside the battery in a separate electrolysis cell. This cell includes several steel plates in series as the negative electrode for zinc deposition or dissolution and the porous nickel in series of the positive air electrodes. Hosseini and co-worker demonstrated the vanadium air RFB system. It was based on a membrane electrode assembly utilizing the Nafion ion exchange membrane as the separator and the platinum IR mixed oxide as the catalyst for the oxygen positive electrode. This system shows the charge and the discharge cell voltage of about 1.88 volts and 1 volts respectively at 2.4 milliampere per centimeter square and 80 degrees Celsius. Organic redox couples RFB. Another hybrid RFB system with separator was developed recently by using cadmium as the negative electrode and a film of organic chlorenyl, that is 90 by weight percentage, as the positive electroactive material. Cadmium was used as the negative electrode since it has large hydrogen over potential. Further, such a material can be easily manufactured from abundant sources. In spite of this, storage capacity is still limited by the solid phase chlorenyl material in the positive electrode. An aqueous organic species, Tiron, was recently studied in a divided flow battery with a lead negative reaction. The system developed with the cadmium chloryl anil shows a round-trip DC energy efficiency of 82%, a low discharge cell voltage of less than 1 volts at 10 milliampere per centimeter square. The last type of RFB which we are going to discuss is lithium-ion RFB. Several lithium flow batteries have been investigated based on the concept of both lithium-ion batteries and aqueous RFBs. The lithium still remains a famous material for RFB systems due to its high energy content of lithium ion. In lithium-based RFB system, the stored energy content of lithium-ion battery relies on the intercalation electrodes as the solid hosts of lithium ions, which shuttle between the negative and the positive electrodes. Hence, the electrolyte in the lithium battery just behave as the ion transport medium, which does not stores the energy. Recently, flowable electrode materials were investigated for lithium-based RFB in 2010, in which the positive and the negative suspensions are circulated through the battery and are stored in two reservoirs. A microporous polymer membrane was used to prevent the active materials crossover from both the half cells. Due to the solid nature of the suspending flowable electrode material, the equivalent concentration of positive electrode suspensions such as lithium cobalt oxide or LiCOO2 and Li-Ni.5 Mn1.5 O4 and negative electrode suspensions such as Li4 Ti5 O12 and graphite are 51.2, 24.1, 22.6 and 21.4 molar per dm cube respectively, which are very large than those of normal RFBs, which are less than 5 molar per dm cube. This provides the significant increase in the energy density, approximately 10 times than that of VRFB. The round-trip Coulombic and energy efficiencies of the lithium flow batteries using Li4 Ti5 O12 negative flowable electrode and LiCOO2 positive flowable electrode were reported to be 98% and 88% respectively. So students, let us summarize what we have learned from this module. According to the phases of electroactive species, RFBs were also classified as solid phase RFBs. Various solid phase RFBs which do not require any ion exchange, membrane or separator, as the chemical energy is stored in an active material or the electrode plates. Apart from this, The redox flow system based on hybrid electrolytes have been described in detail. These hybrid systems involves different configurations compared to the earlier discussed systems. Lastly, in hybrid RFBs, the active material can be introduced or removed from the electrochemical cell without disassembling the cell structure. Further, these systems do not store all of the active material in a liquid or a gaseous form. Hybrid RFBs involves the deposition of solid species or the evolution of gaseous species in one half cell during the charging process. Zinc chlorine and zinc bromine are the best known example of this type of RFB or hybrid RFB. Thank you.